Someone commented that they couldn't hear as well. They needed me to stay near the podium, but hopefully this works better. Okay, so today I'm just going to mainly go through those types of hydrothermal mineral associations that we started to discuss last week. So this will give you a bit better idea of those classifications that people utilise. But it's important to remember that they're a broad classification. They don't necessarily always apply, or the typical mineral assemblage that you associate with it. Some people might not. It might not be there, but they'll call it that style or whatever. So it's a broad sort of idea based on what mineral assemblages are commonly seen. And that's the sort of idea, and it gives you a perception of where you are in the sort of mineral deposit. So we talked about most of this stuff last week. The hydrothermal mineral, the alteration assemblages, depend on the physical and the chemical environment, so pressure and temperature, as well as the composition of the host rock and the composition of the fluid. And then they form the minerals that are stable in that environment. And in an ideal world, these classifications provide a sort of diagnostic set of conditions that they formed in. So that's how it's meant to work. Similar in a way to if you're familiar with the metamorphic facies concept, green schist amphibolite. But in this case, because the system's open, you essentially can get anything you want. So we have to remember that caveat. But it generally works fairly well. So we sort of showed this diagram last week, and today I'm just going to talk a bit more about these types in blue that are circled in blue here, and sort of what do we usually see and what characterises it. So yeah, like I said, these are idealised models. Every system's unique and different, so take some care with that. In reality, there could be multiple or infinite solutions or mineral assemblages are formed, but generally it follows fairly standard types. So this is the broad classification. Everybody loves tables in talks, I know, but we'll get more into it. The handy thing for this table for your sort of knowledge will be thinking about things like temperature, potentially, salinity and oxidation state. And based on these sort of things, they're classified based on typical sort of sources. Okay? So, like a metamorphic, what is a metamorphic one? One up here, it's not overly saline and it's fairly neutral pH. So those things we were talking about during the reservoirs, whereas basinal fluids or, can be fairly saline and might be alkaline. Okay? So those broader sort of features, and as you can see, most of the temperatures are sort of anywhere between 200 and, sometimes you get 650, but generally between 200 and 550. And that's because that's the common realm of hydrothermal fluids. All right? Anything above 650, we're talking about silicate magmatic liquids. So it's generally not that hot, and anything below 200, we're struggling to carry metals and we're struggling to change the environment. We're getting quite cold that, we don't see many mineral assemblages form. So we're operating in this realm of 200 to maybe 550, which sort of coincides with the green schist facies, or the green schist crossing into the amphibolite facies of metamorphism. And most of the things occur in shallow levels, so we do get a broad overlap with common metamorphic minerals, and so that's where a lot of this basis comes from. Okay, so prophylitic, we discussed this last time. This is when they usually go green. So green minerals are forming, so things like chlorite, epidote, maybe some amphiboles. Usually heated groundwater or mixtures of metamorphic and seawater. So they're fairly low in salinity and neutral pHs. It's very common, and part of the reason it's common is because the minerals that form overlap with the green schist facies. So we have to take care. Green schist facies metamorphism is far more common than prophylitic alteration. But we, you know, that's life. We have to get used to it, and there's a broad overlap in their processes. So it's also quite similar to a process here called spilitization. You probably haven't come across that, but that's the process of altering seafloor basalts and mantle material. So it commonly forms pentonite and chlorite and these sort of rocks. And the old timers called it spilitization. That's largely out of fashion now. So we can just say green schist facies. Most of the change is related to hydration, and we can associate it with a broad spectrum of hydrothermal systems. So it's can be, you know, it's not a great, you know, it's diagnostic, but it's not a great smoking gun because it's quite common. So we have to be wary of that. So, but the main thing to realise is it's broadly green minerals. So chloride is a common one, but here's an example. So this is probably a mafic volcanoclastic rock. Overall, you're getting this greenish tinge. Yep, we're comfortable with that. We're getting things like epidote. This is this sort of pistachio green. That's usually the easy way to pick epidote. Chloride's usually quite a dark foresty green, but can sometimes be black. In this case, we've got albitic plagioclase. And the chloride will form from the mafic minerals. Epidote might be forming from some of the feldspars. And yeah, so that's fairly common. So here's chloride. That's its complicated chemical formula, but it's a phyllosilicate rich in magnesium, aluminium, and iron. So it's quite, will take on, if you have a mafic host rock and you hydrate it, chloride's something that's commonly stable. It's happy in that sort of 200 to 500 degrees. It's hydrated, so it's something that comes. But just be wary, we can get different colours of chloride depending on its iron content. So low iron chloride is black or dark. High iron is that sort of greeny colour. So, yeah. And then, you know, if we have some sulphur, we might go pyrite. So we've got some pyrite there, maybe not so much. But here's an example of black chloride versus green chloride. So just be wary of that. And we can also, at high temperatures, get hydrothermal amphibole. They're usually of two types. They're always calcic. And the calcic varieties are usually a mineral called tonalite, which is the common green schist amphibole. So it's a green amphibole, like a dark foresty green, distinct from the brown amphibole that forms at higher temperatures, and tremolite. So they both look quite optically similar. They give a prominent green colour. So prophylitic, usually a greenish tinge. Okay, phyllic alteration. We, for people in the class, we had a look at example of this last week. This is when we usually get muscovites or cerussite, fine white mica. So this is quite common. It's related to the process we discussed last week, the hydrolysis of plagioclase to form white mica. So we're hydrating feldspars and we're reutilising that potassium and aluminium, but we're turning it into a phyllosilicate, so something that can incorporate water. The rock will come sort of a light whitish colour, distinct from other types of alteration. Again, we can be coming to like quartz and pyrite. And sometimes they can be hard due to lots of quartz. Sorry, last week we looked at a geolic one example, didn't we? So we haven't looked at one of these, but yeah. But it commonly calls that whitish colour, and we've got some examples. It's generally high temperatures and prophylitic. Okay. So micas, they're an aluminous mineral. and they commonly break down from feldspars. The muscovite is the potassium-bearing variety. Well, most of them have potassium, but it's very potassic compared to biotite, which also has iron and magnesium. And if it's fine-grained, it's just given another name just to make our life even more complicated. Instead of just saying fine muscovite, it's called cerussite. So when you come across cerussite, just know that that's a fine-grained muscovite. So here's an example of phyllic alteration. We get that broad whitish colour. In this case, we have small K feldspar veins, but in this area where we're getting prominent alteration, we're going this whitey yellow colour, and that's the fine cerussite. So you have to have a hand lens to see very fine intergrowths of muscovite. It's something that you're unlikely to see the prominent books that you see in igneous rocks in this alteration style. And most of the cerussites forming along those vein structures. Okay, here's a bit more pervasive example. The feldspars have changed to prominent sort of cerussite, and it's even more prominent around the vein. Okay, so most of this rock has had fluids percolating. You know, there's some older vein structure here, but this new vein has actually caused even more prominent alteration of that rock in that zone there. And it's, you know, visually you can tell by that stark bleaching in those zones. As another example, we have an early, more pervasive cerussite. It's harder to sort of see because much of the host rock has maintained its structure, or we're having a mixed sort of mineralogy of alteration with the relict phases, and you can still actually see the rectangular form of the feldspar that was originally there. So the cerussite's pseudomorphing it. Then we have this late vein association where we have much more prominent bleaching. It looks like that. Yeah. And here's just a variation on a theme. So you get this prominent white colouring, and you know, in this case we might have some chalcopyrite. Greisen, this is quite a high temperature process. Usually happens in the top of the granitic intrusion, the felsic intrusion, right at the end, and it's a very pervasive sort of ceruttization, and with a lot of silica. So it's a, we usually see lots of quartz, muscovite, cerussite, and sometimes you think things like tourmaline, because there might be boron flushing through that system. So here's an example. It can be quite spectacular, but you can start to see the muscovite is coarser grained. It's a bit easier to see with the unaided eye. Sometimes it can be quite coarse, and you have these rocks that are just muscovite quartz and maybe bits of tourmaline, and they're very hard because you have lots of quartz in there, so they're very hard, and they're common in these late magmatic systems forming at quite high temperatures. Here's another example. This time we've got some tin. So we've got some siderite forming in the vein, but we can see the glittery muscovite and prominent quartz occurrences. So that's a style called Greisen. So it's very advanced phyllic, really, at higher temperatures. Potassic, we showed an example in class, but this is where we usually get secondary potassium feldspar, so orthoclase or adurura, and maybe biotite. So its colours are grey to greeny, and you know, it's relatively restricted in its occurrences, and can form in high temperature late magmatic systems or in lower temperature epithermal systems. So it can be quite a good indicator if you're in a good zone of metallogenesis. And luckily, it's mostly associated with that sort of pinky colour. Okay, so it can be quite a advantageous alteration style to see. So here's an example. This is a mafic rock. So we're getting this sort of greeny colour because we have, you know, original mafic minerals maybe replaced by amphibole. But in this case, we have this pinky K feldspar forming, which is actually breaking down the plagioclase that was in the original basalt and replacing the sodium or calcium with potassium, and we're also getting biotite. And then it looks like we've got quite spectacular chalcopyrite. But yeah, so we're getting this potassic overprint. Here's another example, slightly more prominent. We can see that nice selvage that's a distinct pinky colour versus the rest of that sort of rock, which is some sort of volcanoclastic rock, potentially with a background, maybe prophylitic alteration. This case, it's gone slightly pale white, so we have to take care and make sure we can identify the right feldspars that are stable. But we have, in this case, we have biotite and has an unusual shredded habit, which is distinct from these forms, distinct from the original magmatic that's usually euhedral or subhedral form. So this commonly forms in high temperatures, in oxidizing environments where we can stabilize K feldspar, so it's commonly in the core of these systems. So it's quite a good indicator that you're in a high temperature, potentially good metallogenic zone, whereas the background prophylitic is more of an indicator that you might be getting some alteration in the system and you need to move closer to or higher temperature, closer to the source to find any sort of metal deposit. This example is quite prominent. We get that beautiful pinky colour. People in class saw this last week. We have dark grey veins of quartz, maybe with bits of chalcopyrite and bornite. Here's a lower temperature potassium feldspar called azurura, and it's a bit more porcelain in its form, but in a lighter colour. Okay, sodic alteration, less common. So this one's less it's not one of the prominent sort of classifications, I guess. And it's very similar to potassic, but instead of potassium, we have sodium. Okay, so in this mafic rock, we have a vein. In this case, it's quartz magnetite, but albite is replacing the feldspars in that selvage. So they might have been calcic, so the sodium replaces the calcium in the feldspar. So it's a sort of like-for-like substitution. Here's another broad example. Albite forms commonly that sort of milky or soapy white colour, which is usually the best way to indicate it compared to calcic plagioclase. Here's a very strong, pervasive occurrence, and this rock will be much harder than something with cerussite in it. Okay, because cerussite's a muscovite, so it's lower hardness, whereas this is a plagioclase. So, okay, skarn. This is a this is a sort of tough one because it's also a deposit type. So a skarn is just a word for a calc-silicate mineral alteration style. So when we talk about calc-silicate, we usually, so calcium, aluminium, and silica, probably with carbon dioxide. So calcite or dolomite associations. That's usually what we talk about with calc-silicates. And so we can get quite complicated and pretty assemblages involving garnet, pyroxene, amphiboles, epidote. They're all minerals that can take on large proportions of calcium. So where these usually form is if we have some limestones in the country, in the contact aureole of granite. So they come up, and what happens is if you have a pure limestone and we have these late magmatic fluids that come off the granite, and they might move in new elements into that, something that was, say, calcium carbonate. And they might move in things like aluminium, maybe some iron, maybe some magnesium and things like this. And then that enables these minerals to form, like garnet, pyroxene and amphibole, depending on the pressures and temperatures of the system. And part of the reason this is reasonably common is we have fluids reacting with something that's highly alkaline. So limestone is a highly alkaline rock type, and then we have fluids that might be acidic or of a different redox state, and they interact with something that's highly reactive. Whereas some of the other, country rock is less reactive, so the fluids don't interact as much or deposit other elements. So that's a broad example of a skarn, and you can also actually affect the host granite. So it can internally alter itself, and people call that an endoskarn versus an exoskarn. So endo meaning internal, exo meaning external. So we'll get more into skarns later, but that's the broad idea. So they're quite spectacular rock types to look at because you get beautiful garnet. In this case, garnet's the pinky red. You'll get pyroxene, whereas this case it's a sort of pale green. It's like here and here, and the darker green is the amphibole. And we've also got chalcopyrite here. Maybe hematite. So we go from some sort of pure white rock almost to something that looks like, a Christmas tree. And so altering these assemblages. Here's probably a relatively simpler case. Here's our nice marble, but we have little specks of red, which is the garnet, or the pinky garnet, that has sopped up the aluminium and the silicates, whereas for the rest of the rock it's just calcium carbonate. So depending on how much of that material is introduced is how pervasive this alteration is. Here's an example of an endoskarn, so the internal skarn to the system. In this case we have epidote, biotite, hematite, chlorite, malbite. And so it has a similar process, but we're starting from a silicate base instead of a carbonate base. So we're less likely to see as much calcium carbonate assemblages. What's this one? All right, yeah. Variations on a theme. This is a nice example. In this case we have calcite, garnet, pyroxene, quite prominent. We've got this bladed mineral called wollastonite, which is a calc silicate assemblage that forms at reasonably high temperatures. Another variation on a theme there. Okay, so argillic alteration, we had a look at an example in class. This is the low temperature when we form clays. Okay, there's lots of terms here. I remember argillic bases, you might have come across a rock type called argillites, which is just like a clay mudstone. So this is the same etymology of the wording. So pretty much everything except quartz goes to clay, particularly the feldspars. Remember, feldspars are fairly unstable, and there's usually a gradation in the alteration, and it's mostly associated with low temperature peripheral margins of deposits. It could be late magmatic, epithermal. A lot of deposits can get argillic alteration. And we have to take care because when we have chemical weathering, we might form kaolinite and things like this, and it can be similar to this hydrothermal style. So clays, mostly things with an aluminosilicate with high proportions of water, 8 hydroxyl components, and they're low temperature products of most luminous phases, especially feldspar. Yeah. They're hard to identify, that's life. So you might find a lot of people will identify them by a method called X-ray diffraction or XRD. So you can actually distinguish the different types of clay. So for this work, you'll largely get to deal with the common ones like kaolinite, maybe a lunite and things like this, dickite. Here's an example. One of the obvious features about these is the rock becomes very light and highly friable because it's lots of clays. So most of the feldspars here have been altered. In many cases, we're preserving their shape again, so we're pseudomorphing them. We're getting prominent sort of rectangles where the clay has perfectly altered the feldspar. Here's another example, extremely pervasive. And we might have some iron oxides. This is a tuff. Everything's gone except the quartz. So, sort of classic example, and here's another nice one. This is an andesite. And we have some dark grey areas, which is quartz, but we have prominent kaolinite, and these are actually iron oxides, or iron carbonate, sorry, that have probably replaced some of the mafic phases that were there. Okay, we have another style which is called advanced argillic. So this is like a case where we might have very strong acid leaching, oxidizing fluids, and potentially slightly higher temperatures. We get clays, quartz, sulfates, and iron-bearing minerals, and they can commonly be mineralized. So yeah, they're quite common in the top of porphyry systems or epithermals. Here's a nice example. So we have clay alteration in the vein. So we have white translucent kaolinite and dickite. Dickite is another clay, which is characteristic of advanced argillic alteration. But in this case, we also have pyrite, chalcopyrite, and bornite. So we're getting copper mineralization, iron sulfides, and bornite crystallization. So we might also get things like alunite and anhydrite, so if the system is very oxidized. So here's an example of alunite. So potassium aluminosilicate, but with a sulfate. Sorry, not silicate, potassium aluminium sulfate, a hydrated version. Okay, and then carbonate. This one's largely self-explanatory. We get calcium carbonate involvement. These are the common sort of carbonate minerals. So calcite, our friend, dolomite, where we add magnesium, anchorite, where we add iron, siderite is just iron carbonate. So essentially you flush the system with carbonate and it transforms or binds with these other elements to form these sort of mineral assemblages. And here's a sort of example. And this prominent weathering feature here is the iron oxides oxidizing, or the sulfides oxidizing. And this is just an example of a carbonate altered grey wacky. So we have a lot of anchorite in this example. Oxidized surface. And then in here we have some fresh anchorite. So calcium, iron, carbonate. Which sort of makes sense because we probably had a reasonable amount of iron in this rock to utilise. Here's another broad example. We have feldspars replaced by muscovite and carbonate. And then we also have some sulfide minerals. pyrite and arsenic pyrite disseminated in the rock and then have been strongly oxidized. So this is just a broad example of carbonate. And then the final type is silicic. Again, this one's reasonably self-explanatory. You place it with silica. And this usually makes the rocks completely destructed in their texture and form, and they're very hard. So I think that's the broad ones, but if we go back up to the beginning, we look at things like this. So we've got broad classifications for these types, and you can start to utilize these complicated diagrams a bit better about when chlorite minerals will form, at what sort of conditions in the system in terms of temperature and pH. Talked about potassic, skarn, philic, argillic, and advanced argillic. We also threw in a couple of extras just for good measure. Greisen, which can be sort of considered as advanced philic. And we talked about carbonate and silicic. And then, so if we look at this diagram, here's all our types that we discussed. The main ones to sort of get comfortable with will be propylitic, philic, potassic, and argillic. Right? And then you can sort of consider this greisen as a form of philic, an advanced form, and argillic as an advanced form. And so think about those styles. And then carbonate and silicic are reasonably self-explanatory. Yeah, and so the main thing we do is that we have the characteristic mineral assemblages, which can then start to inform us about these factors, which is telling us about what the system was like, and therefore what was its potential for finding good metals. You know, so was it likely to be carrying gold if it's reduced, or saline and things like this. Okay, so that's the broad idea. Yes, more things to learn, as always.